Hi guys. So it turns out that there are some neural networks that you probably already know. And one of them is linear regression. So linear regression can also be modeled and expressed as a neural network. It can also be thought of as a neural network. Let's see exactly what is linear regression and how can we express it as a neural network. So linear regression, it says that you have some response variable y, and it relates to some covariate x's, which can be d-dimensional, through some coefficients and plus some Gaussian noise. Okay, so the Gaussian noise distributes normally with a mean 0 and some standard deviations. So what it means is that if you add these constant terms, given that you would know the true betas and given a certain x, then the y's will distribute normally with this beta transpose x, and you could take the beta to include also beta 0 and add 1 for the x and sigma squared. So this whole thing is the mean of the distribution for a given x. Okay, and for linear regression, there is a closed form solution, what is called the normal equations. If you do maximum likelihood or ordinary least squares, in the case of linear regression, they are the same, then you arrive to this solution. So you don't have to do any optimization. You just have to take the X matrix, the design matrix, of not only one observation, but all your observation, transpose it, take the multiplication with itself, take the inverse of this, and then multiply this by X transpose Y. And this will give you the estimated coefficient betas, the betas that maximize the likelihood or that minimize the squared error. Okay, so how do we express this as a neural network? So let's look at a case where suppose X is two-dimensional. Okay, so X is two-dimensional. We have, let's say, X1 and X2. And we'll also have 1, which will add and which will have a bias. Okay, and we will have W2 and W1 as the weights or the coefficients. And so we could express this whole model simply as a linear layer. So we could just take x1 times w1 plus x2 times w2 plus b and not have any activation function, without any activation function, and just take this to be the output of our neural network. So architecture-wise, this is the architecture. It's very simple. It's one layer, no activation function, just the linear operations. What about the loss? Well, we can take the loss to be the mean squared error. The mean squared error is exactly like the ordinary least square objective function, maybe up to the constant of 1 over n, but it doesn't matter when it comes to the optimization process. If you multiply by a constant, you will get the same minimum or the same maximum, the same arg minimum or the same arg maximum. And so what is the difference? So we could express linear regression as a graphical model which has layers. So the architecture is the same. The loss is basically the same. What about the optimization? Okay, so here we said we don't need optimization. There is a closed form solution. We just plug it in and we get the solution. But in a neural network, we don't assume that there is a closed form solution. Instead, we do some form of optimization. So for example, we do gradient descent or stochastic gradient descent. And so let's code this up in Python. And specifically, I opened the Google Colab, and I suggest you do the same because it already has Torch installed when you run it. I believe in learning by doing, so I will go over it. I won't give you an introduction to Torch or Google Colab, but I think it's pretty self-explanatory. Okay, so you open up Google Colab, and the first thing you want to do is import a bunch of libraries that help you implement neural networks. So you need Torch and torch.nn neural networks for doing a lot of basic operations. I also import Torch distributions. This is just to help me generate the data. And then I'm also using matplotlib for plotting a little bit. Okay, so I'll run this. Okay, and now let's generate the data. Suppose we have 500 points, and I'm taking X to be uniform, a box uniform in 2 dimensions. So from -3 to 3, 3. And I'm going to sample 500 points from this distribution. Then suppose I know what my true coefficients are. So suppose the intercept, which I will denote W0, is 0.3, and the coefficients, the W true, are -1 and 2. Then I set this up. Then I multiply X with W true, add the W0, and then add the noise terms. Yeah, so this is the noise. I'm calling the normal distribution with a mean 0 and standard deviation or a variance, I'm not sure, of 0.1, and I sample from it. Okay, and doing this will generate the Y's. And now I can create a 3D graph of this. Yeah, so it looks something like this. And the points are more or less on this plane with a little bit of noise. And now let's do regular linear regression. So we said that this is the true solution. So we just have to add a column of 1s to the X in order to make it the design matrix. And then we'll take X transpose times X, we'll invert it, and then multiply it by X transpose Y. And we get that the least squares solution, or the maximum likelihood solution, is 0.29, minus 0.99, and 1.99, very, very close to 0.3, minus 1, and 2, which were the true parameters that generated the model. But again, our data had some noise in it, so we can't expect it to uncover the perfect coefficients unless you have infinite data. And here we only use 500 points. Okay, so now let's do the same thing with neural networks. So we said that neural networks have 3 main components. The first one is the architecture or the model. So this time we have a very simple architecture. It's just a linear layer without any activation function. And so we call NN linear, and we said that the input features are 2 and the output features are 1. Okay, and so this is the graph before. Again, you don't have to specify the bias. It automatically adds a bias. And in fact, you can say, you can add a term that says that you don't want a bias. Yeah, you can add bias equals false. Yeah, but we want a bias here. And the bias is the intercept. So this is all we need to do to specify our model. It's a pretty simple architecture. So let's run this. Loss, we just call NN MSE loss. It's the mean squared error loss. And now we have to do the optimization. We have to specify an optimizer. And for the optimizer, we will take stochastic gradient descent. We have to pass the parameters of the network. We do this by calling our net object dot parameters. And then we also have to pass the learning rate. Okay, so the learning rate is how big are the steps in the direction of the gradient or in the opposite direction. Okay, so we do this. And now we have to do the actual optimization, what is called training. And here I'm going to do it really, really simple without all the extra stuff. I'm just going to run a loop for a fixed amount of steps. And here I set it to 500. I have to, in each step, zero out the gradients because the default is that it accumulates the gradient pair round. So no, we wanted to always forget about the gradient from the previous iteration. I then do a forward propagation. I take my axis, pass it through the architecture to get my output. I then compute the loss. Okay, so I give the loss both the output of my neural network and the true targets, and it computes the loss, in this case, the mean squared error. Then I have to do backward propagation, and this computes the gradients for each weight. And then I have to tell the optimizer, okay, take the gradients and take this big of a step in their direction. And so this is what this does. And let's run this. And now I can look at the parameters of our network and see that the intercept, the bias of the first layer, of the only layer, is 0.29, so very close to 0.3. And the coefficients, the W1 and W2, is minus 0.99 and 1.99. So again, very close to -1 and 2. So this is all for this video. I hope you enjoyed and saw how neural networks can be something actually that you already know, and how easy it is, or relatively easy it is, to program neural networks, especially using all these libraries that abstract most of the operations for us, like PyTorch. Yeah, and I hope you enjoyed, and see you in the next video.